right, cool. So sustaining Git performance under heavy workloads and AI-driven approach. So yeah, I'm Danny. I guess a few people here know about Gerrit and Gerrit Forge, hopefully. For those of you that don't, it's a source code management tool. The main thing I want to talk about today really is it's a fully Git-based, and it's the only one. Might be a bit of a strong claim, but what I mean here is that it is actually it's fully based on Git in the sense that if you're using GitHub or if you're using GitLab, the metadata regarding your code review is actually stored in an external database, while if you're using Git, it's actually stored inside the repository itself. So this does mean that if you're maintaining a repo with Gerrit, it might grow a little bit quicker than if you're using it with other tools. Also, sorry guys, this is bothering me. Yeah, anyway. Also, being fully Git-based, it really gives us some interesting ways in which we can scale to multi-masters and beyond that. So that's pretty cool. If you haven't heard about Gerrit Forge, we're major contributors to the Gerrit ecosystem, and we also help clients globally with the Gerrit installations, which is why we get to see really weird ways in which people are using Git and how they shouldn't be using Git, and yeah, some common problems that they all have. So today I'll quickly talk about what's the problem that we're trying to solve, the current Git repository maintenance strategies, and how we're planning on using AI to help us out. First of all, this shouldn't be a controversial statement in this audience, but I want to start by saying that SCMs are actually the heart of any software-based company, and if your SCM isn't working, nobody in the company is working. So it's quite important that they're up and running at all time. Also, I want to say that modern Git SCMs are actually quite reliable. I hope not to jinx anything, but I don't think anybody here has like daily problems with using GitHub, GitLab, Gerrit. What we started to see is actually it's the Git data itself that is starting to be a bit more problematic. So let's take a look for a second at what affects SCM performance. First of all, you've got the size of the Git repo. Here I've taken the Linux repo, and we can see how the size of the .git folder is actually the vast majority of the size of the repository. It's not monorepo by any stretch of the imagination, but it's significant in terms of percentage of the .git folder taking up space. But also, that's not the only thing. The shape of the repository is also very important, and you have things like the number of pack files, the number of objects that really affect the performance of your repository. So also, with newer trends, we're starting to see that the load on the SCM systems is always higher and higher. There's a bunch of companies, I'm sure here, using them too. There's a bunch of AI review tools, the AI bots that are like adding reviews, making more builds. So the load is only increasing and increasing furthermore. Finally, at least the traditional maintenance operations are actually outdated by the time they finish. So they're not, by the time a git GC finishes, for example, it's already outdated because each new push affects the results of the previous GC cycle and makes it more and more obsolete. And also force pushes, for lack of a better term, kind of void some of the maintenance operations, making bitmap traversal much less efficient. So yeah, we're proposing this idea that traditional Git maintenance isn't enough, and I think Taylor this morning also highlighted that, how they're working really hard on providing new maintenance structures. So what do we mean by Git maintenance? Let's take a quick look. Taylor said it way better than me this morning, but there's different implementations of Git, of course. So you've got JGit and CGit. They do things slightly differently, but generically speaking, they compress loose objects and pack files, they generate bitmaps, they repack refs, they prune old pack files, they create commit graphs, for example, and then we have a few CGit-specific operations like creating or running geometric repacking, generating multi-pack bitmap indexes, and finally generating craft pack files. There's a bunch more that Taylor went over this morning in his great talk, so all of that applies here. However, the main concept is that all of these operations have a cost and a benefit. So some operations have a higher cost, some operations have a lower cost, and they yield different results. So the question that we're trying to answer here is, how do we get the best performance in the cheapest way at that point in time? So talking about cheap, we could just leave the repo grow unsupervised, but yeah, we can quickly see if you run no Git GC maintenance operations or anything really, your upload pack times start spiking really, really quickly, and the repo becomes completely unusable. So at the moment, independently from what maintenance operations you're running, there's not really a better way of doing it other than time or threshold based, right? So in this example, which is a real life example, they were running it on a cron job. So every few hours, they would run a few operations, but we can see how during the working hours, the number of pack files is actually growing in quadratic fashion, while after 5 p.m., when all the developers went home and everybody stopped working, Git was actually able to like catch up with the load and bring back the number of pack files in an acceptable level. But really what we're doing here is we're kind of hoping that that our maintenance operations are going to do the job and it's going to be efficient and somebody's going to like reduce the load on their repo and everything is going to be fine. We kind of want to do a bit more than that. And the reason these pack files are exploding in this quadratic manner is that, say a GC, for example, on one of the monorepos that we deal with could take 45 minutes to an hour, if not more. And during that period, there's going to be a bunch of pack files coming in, making the repo actually less efficient than it was when the GC started. So let's look for a second at why a human can solve this problem. So first of all, it's a pretty complex space. It really depends on like live interactions from clients, from users pushing, force pushes, for example, immediately create problems. Furthermore, there's often just one SRE team looking after different SCMs. And the problem is compounded if you start thinking that we have customers that have GitLab, GitHub, Gerrit, and then they also run different versions of each. And so this poor SRE teams not only has to manage 3 different servers, but also 3 different versions of them. So yeah, finding people that know that much about Git is really hard, and you need to go and find them with a lantern, right? So we started exploring AI for ensuring repository health. We call this product GHS. If anybody here is from England, it's a bit of a play of words on the NHS. We hope it works a little bit better than that. What is happening here? Okay. So let's talking about reinforcement learning is the algorithm that we decided to pick. And we collaborated with Shane McIntosh from the University of Waterloo to give us a hand on the scientific background on this. So in really simple terms, how this works is we have an agent. The agent executes actions on an environment. We observe this environment. We then assess the action that was taken and feedback the result back to the agent so they can tell if it was a successful action or not. So I know that was a bit of a handful, so let's talk about each section independently. So the model that we initially allowed, let's say, our agent to take are no action. So if everything is working fine, why would I need to do anything? It's all going great. We can recreate bitmaps. We can repack refs, for example, although we might start using the ref table backend and this might disappear completely. Another one is removing keep files. And finally, we also tested with geometric repacking, which I'll talk about more in a second. Some of you might notice that we didn't include the full GC as an action for a model. There's 2 reasons for that. One, the main one is that it's a really long-lasting action, so it's really hard to tell if an action that I took now that improves the system an hour or 2 from now is really going to be, why did the system improve in those 2 hours? Is it because of the action I ran 2 hours ago, or has something else changed in the system that has improved that? And finally, also, it's the least vulnerable operation. Everybody can just run a git GC. Why would you need any smartness behind that, right? So now let's look at how we're observing the environment. So before we look at that, we need to try and figure out what is the thing that we're really trying to optimize. So we host a site called Gerrit Hub. If you don't know, go and check it out. So we started looking at on the metrics on that side, what really dominates the traffic on it. And we found that by far and beyond, upload packs are the most common operation. So we decided that that was going to be the most interesting thing to try and optimize. This is because the amount of bots that are like cloning the repo and also just doing builds, doing AI reviews, it's just so much more than what a human can like physically push, right? So yeah, it makes sense that upload packs dominate this statistic. So we then try to analyze what is the best measure of an upload pack. How are we going to know if this upload pack is going to be performant or not, right? You could say, oh, I'm just going to do a git clone, and if it takes 2 minutes, it's better than if it took 5 minutes, right? However, you need to wait 2 minutes or 5 to figure out if the action was good or not, and we didn't really want to do that. And also, there's a lot of variance in there, right? It could be that the search for reuse phase was actually really efficient, but the client has got a really bad connection, so the clone was low, but it had nothing to do with Git itself. So the metrics that we found was the bitmap index misses. So if you're missing the bitmap often, it means you're not using it efficiently. So that needs to be regenerated. And also the number of loose objects and refs, it was another metric that we thought would give us a good idea of in how good of a state the repo is. So after that, we need to assess the environment. So we move to how do we compute rewards for our system. So we divided in three parts. We assign a little bit of a reward for the index misses metric, another little bit of a reward for the search for reuse phase, and finally, a penalty for the cost of the action. Okay, so let's look at each in a little bit of detail. So if we go from a pre-action state where we have no bitmap, and we move to a state where we have created a bitmap, we're going to give a reward that is proportional to the effectiveness of the bitmap. How do we decide if a bitmap was effective? Well, it's a bitmap that reduced the time that the search for reuse phase took. So on the same thread, if we go from a state where we had a bitmap and we end up in a state where we've generated a new bitmap, we're going to give no reward if the rate degrades, as more reward if the rate is unchanged, and a full reward if the rate improves. Finally, this is not really possible simply because we haven't coded it into the agent. Unless they became sentient and decide to do what they want, we should be all right. But if we if we start from a state where there is a bitmap and we end up in a state where there is no bitmap, then we assign no reward to the action, to the agent. So very similarly, calculating the reward for the search for reuse. If we go from a state where it's medium on a scale of low to high, latency-wise, and we end up in a state where it stays the same, then we're going to give a small cookie. If we go from a state where it's high to a state where it's still medium, we're going to give a bit of bigger cookie. And then if we go from a state where it's high to a state where it's low, then obviously we're going to give the agent a full reward. Finally, a bit on the flip side of that, if we execute no action, that's the cheapest thing you can do. You've done nothing, right? So we're going to give the agent a full reward. If we've created the bitmap, it's not an expensive operation, but it's the most expensive operation that we've coded into the agent so far. So we're going to give it no reward. And if it ends up repacking refs, we're going to give it a small reward. Finally, how did we actually implement the agent? So we use a technique called Q-learning, which is quite simple and explainable. There's no complicated neural networks or nothing we don't understand going on. But we start from a discrete representation of the state. So all of the metrics that we analyze, we put them in numbers. We then have what actions did we take prior, in prior situations where we were in this state. And finally, a cumulative rewards of the prior actions. So yeah, how do we then select the action to execute from a certain state? So let's say that we're in a certain state. We're going to exclude the actions that we took in different states, because obviously they're not relevant. And then we're going to pick the action that has the highest cumulative reward in that state. In this case, for example, it's creating bitmaps. It could be, I don't know, regenerating a multi-pack of bitmap indexes. It could be geometric repacking, whatever you want, essentially. So yeah, let's look a bit at what we thought was going to happen. So we plotted the search for reuse over time, and if we executed no action, we were expecting the search for reuse to skyrocket, as we saw earlier. With time-based GC, we would expect the repo to stay a bit more responsive, but eventually also fail. And using our agent, we were hoping to minimize the area under the curve and also the number of catastrophes happening during the experiment. So, and now this I think is really interesting. How did we evaluate this in real life? So we essentially created a separate environment where we could train the agent. So we called it our gym. We put Git on a bit of a treadmill, so improved some aspects of it. That might be a separate talk. And then we use this tool called Gatling. I don't know if people in the room know about it, but it's a load testing framework usually used for HTTP operations. We extended it, and this has been open source for many years. We extended it to support the Git protocol. So it's called Gatling Git. Go and check it out. But essentially, what this is allowing us to do is generate literally years worth of traffic in a few hours. So once we've got that going, and this is both generating write and read traffic. So it allows us to analyze if the clones are improving as well. So once we've got this up and running, we can connect our agent to the environment that's going to execute actions, and it's also going to be able to understand if there were good actions or not. Finally, we decided to deploy, when we get to deploy this in the real world, now the agent has some experience, it's put its tie on, and so it's going to know what to do in most of the situation that it encounters. However, it can keep learning. One thing that I really like about this approach is that there's an element of randomicity to what it does. So when we start training it, it goes off and experiments things. So if it randomly run operations that we've coded into it and figure out by itself what gives the best results and the best yields. So it'll be able to understand in different environments what's the best thing to do. That is pretty much it. Just to give you a final result, this was a real-life example of what we managed to do. So if we're running no GC, we can see that the area under the curve is really high. With running GC, it comes down a bit. And then with our approach called Franco, the area under the curve was extremely, extremely small. So just to recap what we went over today, obviously Git is crucial to your team performance. If Git is not behaving and your SCM is not behaving, your company is not delivering. Server-side maintenance can really have a big impact on what's happening. Also, SREs can't know everything. So we're essentially trying to help them out. And the time or threshold evaluation based on execution of maintenance actions is really not ideal. And we think we can do better than that. So I want the takeaway of this to be is that we've essentially created a framework where we can code in any action, and all of the actions that Taylor talked about this morning, I think would be perfect fits to fit in here. The problem is, which one do I run at what point in time? And that's what we're trying to resolve here. Obviously, this is Git agnostic, so you can use it with whatever. And yeah, just to put this in writing, that's what we're trying to do. So yeah, thanks for your time. That was me. And yeah, hope you enjoyed it.